So what we're looking at here is how to solve problems with units without using formulas. Okay. Throughout the Chemistry 1 curriculum, you're probably going to, if you used formulas, use about 10 to 12 formulas, which you would need to memorize. Because at least here in Virginia, you don't have a formula sheet on the SOL. Alright, so you would need to know those backwards and forwards. What I'm going to show you here is a method to never have to know a formula again. So let's take a look and see how we're going to do it. It's all about units. So if we look at density, alright, something we should be familiar with by now. Finding the mass of 150.0 milliliters of salt water where the density is 1.15 grams per milliliter. Okay. The first thing we want to do is figure out what this thing is asking for. And it says mass. Okay. So the next question then is to identify what unit I need. Well, I've got milliliters and I've got grams and over milliliters, so probably going to be then grams. What I'm trying to do is figure out a way to get grams with these units. Milliliters and then grams per milliliter. Now, so if you've been following along, this probably looks pretty straightforward. If I multiply here, I know I've got milliliters over 1, well then I've just got milliliters and milliliters, they cancel, leaving me with grams. So what does that mean? It means I'm going to set up my 150.0 milliliters and I'm going to multiply it by my 1.15 grams per milliliter, per every 1 milliliter. And this is looking pretty similar to a dimensional analysis problem now. 150.0 milliliters times 1.15 grams divided by 1 milliliter. Milliliters cancel. Let's solve the math. 150.0 times 1.15 divided by 1. You get 172.5 grams. Now, we have 4 sig figs here, we have 3 sig figs here, which means we have to cut off to 3, gives me an answer of 173 grams. There we go. Okay, 173 grams. Let's take a look at the second question then. Okay, finding the volume of 47.0 grams of iron where the density is 7.874 grams per cubic centimeter. Well, here the volume, instead of being in milliliters, looks like it's in cubic centimeters. So I've got to find a way to find cubic centimeters using grams and grams per cubic centimeter. Okay, well, let's try one thing, okay? I can rearrange these however I want. I just need to keep these two things together, either like this or flipped, and I can do whatever I want to this thing. Okay, so let's say, hey, I've got grams on top. Let's try and divide by grams. So what does that give me? It gives me grams over cubic centimeters divided by grams, which really means multiplied by its reciprocal. That means I've got grams over grams, and then that gives me, 1 over cubic centimeters. It's not what I want. Okay, scratch that. What I'm really going to want to do, let me slide this up here a little bit. Okay, so we got a little bit more room. What I'm really going to want to do is take my grams and then multiply by cubic centimeters over grams. Okay, so keep in mind here, this grams is per every 1 cubic centimeter, so if I set this up, 47.0 grams times cubic centimeters, that's every 1 cubic centimeter, and it's got a mass of 7.874 grams. Now it's a ratio of volume to mass. This is equivalent. 7.874 grams for every 1 cubic centimeter also means 1 cubic centimeter for every 7.874 grams. So it doesn't matter the way I set it up. Alright, we're going to go ahead and just do this multiplication now. 47.0 grams times 1 cubic centimeter. So 47.0 grams times 1 divided by what's on the bottom, 7.874, and we get an answer of 5.9 5.69. And to three significant figures, that turns out to be 5.97. Grams cancel. Cubic centimeters. So we just did two density problems, and we didn't even have to think about the fact that density is mass over volume, or the fact that mass is equal to density times volume, or the fact that volume is equal to mass over density, which is really exactly what we did here. We took mass and we divided by the density. We took the mass, or excuse me, the density, and we multiplied by the volume. We didn't need to know any of those. We just needed to follow the units. Let's take a look at another. Here, a couple examples of heat problems. All right, so we haven't done heat yet. In this class, it's going to be the next topic that we cover. Okay, so we're going to show you how to do some of these heat problems without ever having seen the formulas. Got a couple things. We're going to find the energy in joules. Okay, so that's what we're trying to find. And I've got grams, and then the enthalpy of fusion of ice, 334 joules per gram. Okay, required to melt ice. Okay, 25.0 grams of ice. Well, we see here, hey, grams, and then something over grams, all we got to do is multiply. Pretty easy. All right, so we're going to find the number of joules by taking your grams, 25.0 grams, and multiplying it by your 334 joules per gram, so for every 1 gram. Grams are going to cancel. Bring out your calculator here. 25.0 times 334 joules divided by 1. That's going to give us 8,350 joules, which is convenient because it already has 3 sig figs, just like both of those. Let's try another one. We're going to calculate the change in temperature in degrees Celsius if you add 2,700 joules to a 315 gram sample of water. And it says here the specific heat of water, whatever that is 4.184 joules per gram times degrees Celsius. Interesting. So the first thing I want to call it back is when you take a look at this density problem, you notice how we couldn't just stick the one, we needed the thing that we want. The thing we wanted, the cubic centimeters, needed to end up on the top somehow. We couldn't leave it on the bottom and expect it to turn out. That was no good. We needed to flip something around to put it on the top. So that's what I want to call your attention to here. We've got degrees Celsius is what we want, and that's to remind us it's on the top. And here, degrees Celsius is on the bottom. So what we're going to have to do is swap that. Okay, so instead of that, we're going to want grams times degrees Celsius all over joules. Okay, now what we're going to have to do is figure out a way to get joules off the bottom. Well, that's kind of cool because all it needs to take is just a joules multiplied. And then we've got to get a grams off the top. Well, that fortunately we can do by taking this guy. Now, remember, what does it mean when we're multiplying by 1 over something? Okay, and I'm going to put this up at the top. When we are multiplying by 1 over, let's just say z, y times 1 over z, what that really means is y divided by z. Okay, so when we take something and multiply by 1 over something, we're really dividing by it. Okay, so keep that in mind here. We're basically taking these two things, multiplying them, and then dividing by your grams. Make sure that our units check. Joules over joules, going to cancel. Grams over grams, going to cancel. Degrees Celsius on top. So let's plug it all in, see what we've got. We want joules, so your degrees Celsius. Change in temperature is delta T. You're adding 2,700 joules. Okay, so that's going to go up here, 2,700 joules times 1 over 315 grams times, now then we flip this, we see joules is on the bottom here, so we're going to need to put joules on the bottom there, 4.184 joules, and that's 1 gram times 1 degree Celsius. Remember, anytime we see per, it just means one of that thing. So again, let's keep this in mind. Joules cancels, grams cancels, just degrees Celsius. Let's find a number. 2700 times 1 times 1 times 1 divided by 315 divided by 4.184. And so my delta T here is 2.0486 We have a total of 3 significant figures here. Cut it off there. Delta T would be 2.05 degrees Celsius. So now, we didn't need to know that in our heat problem, Q for heat is equal to mass times delta H, which is enthalpy of fusion. Okay, we didn't need to know that, but it's what we did. Just multiplied. And we didn't need to know that, and this is going to take a little bit more space here, so bear with me on this one. I'll scoot this one down. We didn't need to know that, in this case, Q equals M times Cp times delta T, where Cp is the specific heat, delta T is your change in temperature, and then we're trying to find mass. Well, let's see what we got to do to find your delta T. You're going to have to divide everything here by M times Cp. So you get Q, which is in joules, over at mass over specific heat. That gives you delta T. Let's see what units that is. Joules over grams times joules per gram degree Celsius. Going to give you degrees Celsius. Okay, isn't that just what we did? We took joules, we multiplied by 1, we divided by grams, and then we divided by joules per gram degree Celsius. Oops, sorry, let me scoot that up a little bit. Alright, we did exactly that, and we didn't need to know a formula. Alright, solved a problem you've never seen before. So let's take a look at one more. And this is a problem about gases, okay, which is something that we're going to see towards the end of the year. Okay, and this was a little tricky, all right, but bear with me on it. So, given that the universal gas constant R, don't worry about what it is, just look at the units, has a value of 0.0821 liter atmosphere per mole Kelvin, what pressure is exerted by 2.50 moles of gas occupying 4.0 liters at 455 Kelvin? Huh. Well, let's go through here. I see Kelvin, Kelvin. I see moles, I see moles. I see liters, I see liters. The only thing that I don't have is atmospheres. So I'm going to assume that pressure is in atmospheres. And atmospheres is what I'm going to want to end up with. Well, fortunately, I already see atmospheres here. Okay, so I'm just going to leave this the way I found it. Liter atmosphere per mole Kelvin. Well, I have moles, and I have moles on the bottom, so I'm going to want to multiply by moles. And I have Kelvin, and I'm going to want to multiply by Kelvin. Now, this whole liter thing, I'm going to cancel it out somehow. It's on the top. I want to get rid of it because it's not here. So what I'm going to do is multiply by 1 over liters. Remember, multiplying by 1 over x, it's really the same as dividing by x, right? So really what I'm doing is I'm taking this R, I'm multiplying by the number of moles, I'm multiplying by K, and I'm dividing by my number of liters. Let's see if it works. So I'm trying to find atmospheres, pressure, okay? And I'm going to take my numbers now, 0.821 liter atmosphere for every 1 mole times 1 Kelvin. I'm going to multiply it by my number of moles, 2.50 moles times 455 Kelvin, times 1 over 4.0 liters. Let's see if all the math works out. I see liters on the top. Both of those are over 1. I see moles on the top and bottom. I see Kelvin on the top and the bottom. We're just left with atmospheres. Let's find calculator answer at least. Scoot all this over. 0.0821 times 2.50 times 455 times 1. And then we're going to divide by 1, divide by 1, divide by 1, divide by 1, divide by 4.0. Now, when you get to this point, you're probably not going to need to divide by 1 and multiply by 1 and do all that. It's just for bookkeeping at this point. All right, but when we get all that together, we see that to two significant figures, we have the answer 23, and what's left over is atmospheres. And to do that, we didn't need to know that, I'll find a different color here, we didn't need to know that our formula was PV equals nRT. To solve for our pressure, we would have to go pressure equals nRT over V, where N is moles, the gas constant is R, and then we got temperature in Kelvin, and then divide by volume, which is in liters. We didn't need to know any of that, but we still see moles cancel, Kelvin cancel, liter cancel, just atmospheres. You can solve a problem, and you don't need the formula to do it. Okay? So practice your units, pay attention to your units, and you are going to be a much happier camper.